Hello everyone. My name is Irene Ortiz, and I'm doing the PhD under the supervision of Manuel Soler and Javier Garcia Eras in the Aircraft Operation Lab. It's named Artificial Neural Networks for the Detection of Contrails and Aviation-Induced Cloudiness, and is also aligned with the European project eContrail. So first of all, I will show you this nice video that I took when I was coming to uni a few days ago. You might be wondering what are those and how do they form? Well, I will explain it to you, but first let me tell you that you are not being sprayed and those are not chemtrails. Those are aircraft condensation trails, also named contrails. And how do they form? Well, first you need a region of air with the necessary conditions for an aircraft to go by, and when the water vapor emitted start condensing upon soot and pre-existing aerosols, then water droplets start forming, they start growing, and due to the low temperatures, they form ice crystals, and then you see an ice cloud like this one here. And you might also be wondering how long it persists. Well, it depends on whether the air is supersaturated. If it is not, it might only last for seconds, but if it is, it might last for minutes or hours. And in this case, this is really a concern because they have some radiative effects. Indeed, contrails, they trap some of the outgoing thermal radiation from Earth, and they also scatter some of the incoming solar radiation. And on global annual scales, the net effect is warming. Indeed, they are the largest impact of aviation. They account for about 2/3 of total aviation emissions. However, they are subjected to a really large uncertainty, and this is mainly the motivation of my thesis, try to understand better what is the contrail impact, and with this information, we could also inform stakeholders to take climate actions. So a bit of the state of the art on contrail detection. I will be focusing on geostationary satellite detection because they provide global coverage and a very high temporal resolution. So before 2023, most of contrail detection was made using. Sorry. Cool. Okay. Okay, before 2023, most of the contrail detection was made using traditional image processing for line detection. However, in 2023, a large dataset with more than 22,000 labeled contrails was released, and now we can train neural networks to identify contrails. However, there are still some limitations because in satellite images, if a contrail is above or embedded in clouds, it's really hard to see, and if it's evolved or diffuse, it might look like a natural cloud. And also, another issue is there's a lack of a validated data set in Europe, and all of our studies will be focused on Europe. So the state of the art on the radiative forcing part, well, there are some large-scale estimates that suggest that the net warming effect ranges between 34 and 74 milliwatts per meter square. However, they are made with a Lagrangian-based simulation model that lacks validation, and this also motivates the start of my thesis, the need for observational methods. So the goal one would be focused on the detection. We need narrowband measurements from satellites. We take some of the infrared bands, make some RGB false color composites, and then we get an image like this in which contrails are highlighted due to the temperature and the absorption of ice crystals in those infrared bands. And the idea would be to develop methods to identify linear contrails, but also try to, at some point of my PhD, also identify those embedded or above clouds, and also those that are evolved. Then, as for the radiative forcing, the main goal would be to attribute some shortwave and longwave radiation to each contrail pixel, so we can develop some large-scale studies, also attributing errors to this method. And some of the milestones of my PhD, the first one is starting. Then First, I went to the EGU conference, and also I released my first journal paper. Those were in the same topic, which were the development of some AI models for detection. So I trained several models and assessed the performance using this data set, and then I also fine-tuned them and applied them for our large-scale studies in Europe. Then the next milestone, another milestone was going to the Cesar Innovation Days conference. And here I already applied these models to do a large scale study focusing on 1 week on 2023 and another on 2024 and comparing the radiative impacts of contrails in all Europe. So as expected, daytime contrails have a shortwave and a longwave effect, and the net effect was cooling, and nighttime contrails had a net warming effect. However, since this study was performed in January when we have less daylight hours, the net effect was warming, and we found a highest impact in 2024 than 2023. Then the next milestone, I went to the EGU conference this time in 2025, and here I presented a comparison of this method for large-scale assessments with the physics-based model that I mentioned before, which is state-of-the-art. And we got 1 whole week in 2025, and the main findings, there's a large disagreement in some of the optical properties derived with the physical methods because it computes microphysics, while our method computes large average over pixels, and this results in a discrepancy in the magnitude of the radiative flux values, and this is something I'm working on right now. And also the differences due to the interactions with clouds. This is me right now, 1 year and 10 months of the PhD, and some of the next steps I will mention. First, I need to get some of the final results for the contrail project, which will eventually result in a paper, hopefully. And this will be associated to a large-scale study, but this time with 1 year of data, the whole year 2023, and 1 month of 2024, which is an extension of the previous 2-week study. And I already have some preliminary results, but I'm working on it. And we find that in January we had the warmest contrail impact, while in June we had the coolest contrail impact. And also at some point I should do a research stay, and most likely I will be investigating this discrepancy in the radiative forcing and optical properties with other studies, and also try to quantify the errors of these methods. And okay. No se mueve. Okay, no. Yes. And also some of the work that I have ongoing and that I will do in some next steps of my PhD is try to enhance the AI contrail detection models, as I said, to not only detect linear contrails, but also those evolved or diffuse, because right now when I apply the contrail detection model, if it's an old contrail, we cannot detect it. However, if we employ a different approach, like a PIN, which includes physical information on the advection and the diffusion of the plume, we could eventually detect a larger amount of contrails. And also we could test alternative false color RGB products to identify contrails that are embedded or above clouds or alternative satellite instruments. And at some point, I will finish the PhD. And this is a summary of some of the milestones that I just mentioned. I went to these 3 conferences and released this paper that I am working on the review. And this is all. Thank you.